Hi guys, today we are going to be going over a concept about particle distribution across the membrane. So first, we're just going to kind of go over uniform distribution, and this is just simple diffusion, which means that no energy is required. So we're going to start at a high concentration and it's going to diffuse down to space where there's not much over here. And once it diffuses, it'll look like this where it's in equilibrium. And these factors all affect the speed at which it reaches equilibrium. So as we go down here and we look at diffusion across a permeable membrane, we can see that these are all time to equilibrium. These are all effectors, and this is a great chart that can help us. And I wrote down here that this plot, compartment one is dropping. So that means that as we can see here in time A, because our molecules are moving into compartment two. So they're dropping out of box A, moving into compartment two. So that's why compartment two is rising and compartment A is dropping until they reach equilibrium, which is with time C. So then, as we move down here to our rate of diffusion through membranes, we see that our nonpolar molecules diffuse more readily, and that is like our most permeable. So we have here an example. So these are all examples of small nonpolar. And so those are going to diffuse most readily. If we go down here, we see our ions, and these are going to move through ion channels. Because they're polar, they need something to help them get across the membrane. And so here we have our ion channels. How do polar molecules get across the membrane? And additionally, large polar, so right here, large polar have transporters. And I'll have a little visual on that in a minute. But as we go down here, we can see that this is kind of what the ion channels look like. And so if we zoom in here, our number two, these are going to be polar. And that makes sense because we want our ions to get through. So we want them to allow our ions through, but it has to interact with our phospholipid bilayer, which is nonpolar. So therefore, this is going to be non-polar. So the outside is non-polar so that it can interact with the membrane, but the inside is polar so that our molecules can flow through. So as we move down here, this is just showing us our electrochemical gradient. So as we get through our electrochemical gradient, we know that our concentration gradient, as we went over in the first slide, if there's more on one side, it's going to flow to the other. So that is our ion concentration. And then our membrane potential or a voltage is with our sodium plus or potassium plus. So that's going to affect our voltage. And both of these come together to make our electrochemical gradient. So as we move down here, we can see our mediated transport. So this is where you have one molecule bind first, and then after it binds, it gets let out on the other side. And so here, your binding affinity is really going to rapidly drop. So I'll write that down. Our binding affinity drops after the transporter opens, which makes sense if you think about it because our binding affinity has to drop so that this molecule can move outside. So it's going to have high binding affinity so that it will bind and then it will move outside and the binding affinity will drop. So this is kind of my depiction of our channel versus transporter. Our channel just allows a lot of ions to kind of go through like a bridge, but our transporter has limited space. So if we move down here to our mediated transport, we have our uphill versus downhill depictions, and we can see, okay, we have our diffusion, and then we have our mediated transport with our transport, and so that could either be facilitated diffusion or our active transport with our pumps. And so we know that this is down the gradient, because it's diffusion, and then this is going to be up the gradient. And if it's up a gradient, then it needs ATP, whereas our diffusion does not need ATP. So if we move down here, oops, sorry, to our secondary active transport, we can see that we have used an electrophysical or electrochemical gradient instead of ATP phosphorylation, and it's coupled to the movement of another molecule. So then this is a better depiction of it, and this shows how we have our sodium that flows downhill, and then our here, there we draw that. So our sodium flows downhill, and then our X concentration, which is just a different molecule, maybe like glucose or something else, we could say maybe glucose, and that's going to flow up its gradient. So normally it would need like ATP, but it so uses basically momentum from sodium because sodium flows so easily down that gradient. So it could either be cotransport where it flows together, or it could be countertransport where it flows opposite.